Hello everyone, and welcome back to this series about few-shot learning. In the second episode we are going to see which are the most common datasets used in few-shot learning. And I would like to start with the standard datasets used in supervised learning. And we will see why we cannot use these datasets. So the dataset I want to start with is the NIST. It's a pretty common one, you probably know it. And these are handwritten digits, 60,000 handwritten digits, and there are just 10 digits in total, and these are the digits from 0 to 9. These have been written by different people, so they may have different shape, different stroke, and so on. And so why we cannot use the NIST in few-shot learning? So since we have 10 digits, it means we have a total of 10 classes, right? So one important limitation of this limited amount of classes is that it's difficult for us to build the task, a large set of tasks, right? Every time that I build a task, for instance, if we are in the standard five-way setting, it means that I need for each task I need 5 classes, so I have to pick digits from 5 different classes, and there are 10 classes in total. So it means that if we replace 5 with j, this j in this case, if we are using the NIST, has to be less than or equal to 10, right? That are the total number of classes, and this is a problem, right? So in particular, we can actually estimate how many permutation we have here. So let's suppose that we have n total tasks, possible tasks, permutation of tasks. So if we have 10 classes and we want to do a 5-way setting, so if we randomly pick a first digit from the 10 classes with a uniform distribution, we have 10 possibilities. Then one class has been ruled out, we have to pick another one, so we have 9, then we have 8, we have 7, and we have 6. Now if you estimate this value, to find out that this is probably close to, is around 30k, so you will have around 30k possible permutation of tasks that you can get with 5 in a 5-way setting. This is not a lot, right? So when you start to train your method, after a while you will reach this number, and after you reach this number you will start to see tasks that you already saw before, and you will have the usual problem of possible overfitting and so on. So we don't want this, and this is why we generally use another dataset that is called the Omniglot. So the Omniglot is a sort of orthogonal to the NIST, since we have many classes and for each class we have a limited amount of characters. In this case we have a total of 1623 handwritten characters from 50 different alphabets. And from each alphabet, for instance from the Greek and Bengali here, you can have a different number of characters inside, different number of symbols, because the different alphabet may have a different amount of symbols, right? This is normal. And you can aggregate your support set, randomly picking one character from different alphabets, but you can also consider each character actually inside the same language as a different class, so you may also can pick for the same task the same character from the same language. And if you're going to give a look to this website, Papers with Code, there is an interesting chart about the accuracy obtained on the Omniglot in the 1-shot, 5-shot setting. So you will see that the accuracy is pretty high, and in particular here you see that MAMMA, that is MAMMA, there have been huge improvement in the last year. So if with a standard MAMMA we can reach 99.9% accuracy, this means that the Omniglot is no more a good benchmark, right? We are reaching the top here. We want something better. But still interesting to know how the Omniglot works. So in the next slide we are going to see how is the structure of the Omniglot, because many papers today still use the Omniglot as a standard starting point, and then they use something more complex. And also if you give a look to old papers, you may find that often they use the Omniglot, so it's good for you to know how the Omniglot is structured inside. So if we are going to use the tree command from the Linux terminal, in the image folder of the Omniglot you will see 50 directories. So these 50 directories correspond to the 50 different alphabets in the Omniglot. And if you are going to open one of these folders, for instance the first one here, you will see that the first one has 20 directories, and these 20 directories are the 20 different characters of this alphabet. We can then open another folder. Let's say we open the Greek language folder. You will see that in this case we have 24 directories, so 24 different characters. This is different from the other. As I told you, each language may have a different number of characters. And let's say that now we are going to open, always using the command tree, the first characters from the Greek language. You will see here that there are 20 images. There are this one. And these are the 20 images written by different persons. And for instance, the first one here, the first person drew this alpha here. Alpha is the first character in the Greek language. The second person wrote here the second image, and so on. So each person may have a different handwriting, right? So the alpha can be a little bit different. But you can see here other 4 folders, and it is possible to do data augmentation on Omniglot with a rotation in this case. So you can do a rotation 90 degrees, rotation 180, rotation 270. You can basically generate 3 more characters from the first one. And each one of these column here, you have to consider this as a different class. So this rotated alpha here is now considered as a different class. So we have managed with this simple trick to increase our datasets from an initial 1623 characters and therefore 1623 classes to a total of more than 6000 classes in this case. So now we have a huge amount of classes. This is pretty different from the NIST dataset. There is another dataset that is pretty common in future learning. It is the CAP dataset. CAP dataset consists of 200 bird species that are considered our classes in this case. A standard split is 100 for train, 50 for validation, and 50 for test. And if you are going to open the image folder with the tree command, we will see that there are 200 directories. This corresponds to the 200 classes that we have. And if you are going to open one of these folders, for instance this one, we will see that these kind of images are inside. So as you can see, these are pretty complex images. You have different background, different position of the bird in this case. It can be pretty difficult to distinguish between this and this and this, for instance. So it's a pretty good dataset. Another dataset is the mini-ImageNet. This is also very used nowadays. It is probably the most difficult datasets for future learning. Here we have 100 classes taken from the ImageNet dataset. The standard split today is to divide in 64 for training, 60 class for validation, and 20 for test. So why we need a validation set? Because we can use the validation set to choose during training the epoch or iteration where our method was performing better, save the model, continue the training, and then use the best model on the test set. In this way we don't access the images in the test set. This should be standard practice in machine learning. And here you can see some example of images taken from the mini-ImageNet. If you see this one, for instance, the flagpole, here the flagpole is located in the center of the images. It's just a tiny stick in the center of the image. But in another image, actually, this can be observed from a completely different perspective. So it may be very difficult sometimes to identify a flagpole. And you can find This type of complex image is also in the other classes, so it's pretty difficult sometimes to identify the object for the in this setting, especially because if you are in one-shot setting and you are given just this image, it's pretty difficult to understand what should be the main focus of the image and guess to which class in the query set this image may belong to, right? That's pretty hard. Then I would like also to briefly talk about the regression case. So until now we talked just about the classification setup, but we can also do few-shot regression. And they are not very standard benchmark in this case. One has been proposed in the paper about mammal. So in this paper has been proposed to use periodic wave prediction. So you can imagine to have a Cartesian plane here, and then you have a sine wave or a cosine wave, a periodic function, okay? You can use a periodic function to generate a wave, and then you can also translate this wave on the x-axis. You can change the frequency of the wave. You can do many things. But the idea here is that you pick some random point along this curve, right? And this will be your support points. Let's suppose that we have five points, and at training time you're also given the label for the query points, but actually at test time you may get some query points on this curve, and you have to predict, given for instance the x-axis, you have to predict the y-axis in this case. You have to predict it based on the given coordinates of the yellow point, of the support points. So this may be pretty difficult. There are some variation here because, for instance, I can train the method just on a specific portion, on a specific range on the vertical axis. So for instance, I can consider just the portion between 0 and 5, but then at test time I may try to see if the method performs well when we go outside this range. So if we go between 5 to 10, what's going to happen? So if I want to predict something outside the range, can the method do this? So is the method able to generalize outside this range? These are nice questions in the regression setting. There are not so many papers actually in few-shot learning about the regression case, but we will see something later on. So that's pretty much it for this episode, and thank you for watching.